so much for the invitation. It is so daunting to imagine trying to keep up with the coolness density of the previous two presentations, and I really can't do that, but I'll do my best to present something interesting here. So I'm talking about an idea called natural induction, and if I can get my slides to advance, which is not happening. This is a principle of adaptation that might apply from inorganic viscoelastic networks through cells to societies and perhaps to the biosphere as a whole. But we should start at the beginning. So natural selection explains creative adaptation in biology. Well done, Darwin. And it applies at all sorts of different scales of biological systems, from individual self-replicating molecules to single-celled organisms to multi-celled organisms, and in some special cases to colonies. Dawkins pointed out that, well, or rather put into words a widespread belief that the principle of Darwinian evolution is not merely as a matter of fact the principle that explains all biological adaptation here on Earth, but it's the only possible way that something can improve itself. It's the only mechanism of creation. Nothing in the universe gets better or becomes more adaptive or improves except by that mechanism, unless it's designed, but then it's not by itself, right? That means that the mechanisms of natural selection, self-interest and competition, are not only natural, that's how it works in biology, but they're logical, because that's the only way that it could work. And it slides a little bit into necessary and desirable in order for something to improve, but we'll come back to that point later. The point is that that idea that Darwinism is the only principle that can produce adaptive change puts Darwin on a pedestal, and that's what I'm using by that image. Is I'm not criticizing Darwin, I'm criticizing Darwin put on a pedestal. So Darwinism can also apply, those principles can also apply to systems that aren't biological, like firms or organizations or businesses or ideas or memes on the internet or religions. But that exclusivity principle of natural selection places strict limits on the kinds of things that can be adapted. Specifically, if natural selection doesn't apply, a system can't be adapted. And that means that although all these kinds of things maybe can be adapted, these kinds of things can't. Loose social groups, societies, economic markets, cities, ecological communities, the biosphere as a whole, if you don't have a population of entities that's reproducing with heritable variation and reproductive success, then they can't exhibit natural selection. And since natural selection is the only process by which anything can be adapted, those systems can't be adapted. The components within them can, and they might be complicated, but they can't be organized for holistic adaptive function. See debates from group selection, Gaia, critiques of the extended evolutionary synthesis, etc. So my claim is that the universal Darwinism idea is not correct, that evolution by natural selection is not the only possible mechanism of creative adaptation in the natural world, and I want to introduce natural induction, which is not the same as natural selection. So that's coming up soon. Just to give a sort of really quick high-level idea of how different selection and induction are, well, selection, as we all know, we can think of that as separating the things to retain from the things to discard, and the differential reproduction of the things that remain. It starts from a population of things which are different from one another and self-reproducing. Induction, on the other hand, starts from a population of things which are all in interaction with one another. They're all in relationships with other things. And the way that the system changes is not by deciding which things to keep and which things to discard, but by changing the nature of the relationships between things. And as those relationships change, it changes the organization of the system as a whole, and, I want to suggest, produces intelligence that occurs at the system level. So, back to the claims. Natural induction is a process by which a dynamical system becomes adaptively organized spontaneously. It's natural. It occurs in dynamical systems with suitable properties that haven't been selected or designed for the purpose of exhibiting induction. And it explains how dynamical systems that are not evolutionary units, including ecosystems and societies, can learn, adapt, solve problems in a quantifiable sense. Not just a hand-wavy, it's self-organized thing, but actually give it a problem, solves the problem. Okay, so we better start at the beginning. What's induction? Induction is, in logic, is the production of general rules from specific examples. So a specific example, this colorful thing tastes good. Another example, that colorful thing tastes good. Conclusion by induction might be colorful things taste good. Or this one is white, all swans are white. Now, you'll notice that conclusions from induction do not follow logically from the observations. They can be wrong, right? Even if your observations were true, the generalized rule might not be. So why would you want to do induction? Well, induction is fundamental to any kind of learning. Learning without induction means that you can do well on the examples that you've seen before, but that's just memory or rote learning. Learning with induction means you can do well on the example you've seen before and on other novel cases. That's proper learning because it has generalization. Well, we can do that. How do we do that? Well, for our brains, it might be complicated how we do that, but in artificial neural networks, there are some very simple principles that can provide that kind of learning. Associative induction, or just learning what things go together. And this only requires very simple local rules, neurons that fire together, wire together, which more generally, if we take it sort of substrate independent, means that the more two things co-occurred in the past, then the more they become likely to co-occur in the future. Positive feedback on correlations. Now, in artificial neural networks, that really simple principle can do all sorts of cool things. Associative memory and recall of multiple patterns, classification, reinforcement learning, generalization, building low-dimensional models of high-dimensional data sets, and learning to improve the ability to solve constraint optimization problems better with experience. So, brains are evolved to do induction, and machine learning systems are designed to do induction, but that's not what I'm talking about. I'm talking about systems which do induction spontaneously, induction which occurs spontaneously in dynamical systems with suitable properties. So natural induction is the change in the connective organization of a dynamical system that results indirectly from its history of experience or forcing from the external world, resulting in changes in organization which constitute learning and increased optimization ability. Well, I better explain how it works. Well, it's not so surprising that things like brains that are selected to do induction can get better at solving problems with experience. They can exhibit global adaptation ability in networks of simple components. So the individual neurons are simple, but by changing the connections between them, we can get them to solve problems better with experience. And what we have here is just 4 steps to get from something as simple as a mechanical system of a spring that's slightly imperfect to get up to a neural network that learns to solve problems better with experience. And the steps are that, well, that kind of global adaptation ability can be provided by unsupervised distributed associative learning. That's a picture of Donald Hebb, which doesn't require any centralized control or global feedback. And that unsupervised distributed associative learning, like Hebb's rule, that's just positive feedback on correlations. And positive feedback on correlations, well, that comes naturally from any dynamical system described by connections that are viscoelastic. Viscoelastic just means connections that give way slightly under stress. So if I can make those links, I can get from networks of viscoelastic connections to something that learns like a neural network does without selection or design. This will apply to any dynamical system that's described by a network of viscoelastic connections experiencing episodic stress or perturbation, and I'll come back to that point. The viscoelastic means that the connections give way slowly or a little bit under stress, and it's important that the stress in the connections of the network is differential, meaning that it doesn't apply to all of the connections. It's not simply that all of the connections give up, it's the ones which are under stress that give up or ease those frustrations over multiple episode or experiences. And that results in an associative memory of past experience which is held in the connective structure of the system. And because it's associative, because it's in the connections rather than in the particles, it can generalize in the same way that a learning neural network can, and finds better solutions to constraint optimization problems with experience. And that's what I mean by exhibiting systemic intelligence, the ability to find more harmonious configurations that resolve more internal conflict. Okay, so that's still at a high level stuff with quite a bit of jargony stuff chucked in, so let's see if I can explain that in a bit more detail. Here is a set of simple binary patterns. Induction requires that we model some underlying regularities in those patterns. Associative induction means modeling what things go together, which we might do with Hebbian learning, where we have a point in a correlation matrix which represents the positive or negative correlations, pairwise correlations between the features in our patterns. So we might notice that the first two bits in all these strings are positively correlated and the last two bits are negatively correlated. So that's one point in model space is able to represent many points in our original feature space. And we can recall those patterns from our model, and we can store patterns into our model. But importantly, that one point in model space may also produce other points in feature space that weren't in our training set, and that's what we mean by generalization. Okay, now I'm laboring that a little bit because I want to make sure that we can do that transfer between what we already know about learning and generalization in artificial neural networks, which are usually quite sophisticated, but I want to bring it down to something really, really basic that's just about positive correlations. Sorry, noticing correlations. So we can get a dynamical system to be a model of some correlations that we've observed, or we can get a dynamical system to generate patterns from a system of correlations that we've put in it. I describe those two different ways separately. So here's a system of observations, a set of observations. Here's a dynamical system with some variables and some connections between them. And we can put connections between them with Hebbian learning, for example, that represents whether the features have been positively or negatively or strongly or weakly correlated. We might do that in a Hopfield network, for example, is a good model of such a dynamical system, which has been used to model all sorts of things from gene networks to neural networks to ecological networks. Now, if we run that dynamical system, that's a model of the correlations that have been observed, then we have an energy function that describes movements in feature space. And if we start from a random configuration in model space and run the network forward, it leads us to an attractor, and that attractor is one of the patterns which we have stored in the network. If we repeatedly relax the model from random initial conditions, we get a distribution of samples from the model, which are the training patterns that we stored. Okay. Now, a different way to think about a dynamical system is, instead of saying, well, these are the observations, I'm going to use Hebbian learning to put those correlations into my dynamical system. We'll think about it this way. We'll say, I have a problem that needs solving, and in this problem, these two variables need to be the same, and these two variables need to be different. And it's important that these ones have this relationship, and it's not so important that these ones have these relationships. And those are the constraints of our problem definition. And if we treat our dynamical system in that way, when we run the dynamical system like we did just now, what it does is gives us a locally optimal solution to that constraint problem. And if we repeatedly relax it from random initial conditions, it finds a distribution of locally optimal solutions to the constraint problem. This is 1980s Hopfieldian tank stuff. Okay, so those two ways of thinking about Hopfield networks, that we can use them with correlation learning to store patterns, and that we can, the other way is that we set the interactions to represent the constraints of a problem and then run it to solve the problem. They have not been put together before, even though they were both done by Hopfield. So I had to email Mr. Hopfield and say, have you really not put those two things together before? He said, no, I haven't put those two things together before. And maybe that makes sense, because why would you put those two things together, right? One is about storing patterns, it's a model of memory, and the other one is about solving problems. And if you were to start changing the weights in the thing that was supposed to be solving problems, that would be like changing the problem. You're not supposed to change the problem, you're supposed to solve the problem. But actually, if you put those two uses of a dynamical system together and apply them on different time scales, what you get is adaptation by induction, which gives you an improved optimization ability. So let me see if I can explain how that works. So let's start with a dynamical system where the constraints between the variables represent the problem. Running that, you can see, you guys that can do that cool graphic stuff, I wish you could do that for my talk. You can see it would be so, like, it's so crying out for that. Anyway, I haven't got that. The dynamical system, you start with the interactions that represent the constraints of the problem. You run the dynamical system multiple times from random initial conditions. It gives you a distribution of locally optimal solutions. You take that distribution of locally optimal solutions and you use them as training patterns to update the interactions in the dynamical system. And then you go around again and you go around again. Now, when you start updating the constraints in the dynamical system, that's going to start changing the energy function of the system. That positive feedback on correlations is going to modify the energy function. But which way does it modify it? It seems like that's a stupid thing to do. If what you wanted was good solutions to the problem, why would you do that? When you deepen the energy well of a pattern by training on that pattern, it just makes the system more likely to go to that pattern again. And if it already wasn't very good at finding global optimum, and instead it had just found a local optimum, then increasing the basin of attraction for that local optimum just makes it more likely to go there again. It's not going to solve the problem better. But we've missed a trick. That reasoning has missed a trick, which is that there's generalization going on here. And if you generalize the patterns from a set of locally optimal solutions with an associative model, it increases the basin of attraction for the locally optimal solutions that you've already visited. But it also increases the basin of attraction for some patterns that you haven't visited before through generalization, including patterns which are particularly good at solving the original constraints of the problem. So the red one there is a new solution that hasn't been found before. It's the generalization of the ones that have been found. And now, starting from a random initial condition that we started with before that used to go to the left, now it goes to the right. And indeed, the only basin of attraction in the system now goes straight to the global optimum. Okay, so that's how you use unsupervised associative learning, which is just positive feedback on correlations, to make a network of simple components get better at solving a constraint optimization problem over time. The next step is we need to show that that's natural, that we don't need to do a Hebbian learning process in a neural network or hot field network to do that. We can do it in a system of particles connected by springs. So it doesn't need any fancy learning mechanism or algorithm. It only requires positive feedback on correlations, which means the more two things co-occur, the more the connection between them changes in the manner that makes them co-occur more. Such positive feedback will occur spontaneously in any dynamical system described by a network of viscoelastic connections, or interactions that give way a little under stress. Natural systems, natural dynamical systems, relax connections. That's what they do naturally. You don't need to engineer them to do that. And when they give way, they oppose less. They become more consistent with the current pattern of forcing determined by the state variables, which makes the current pattern of forcing more likely to co-occur again. That's the positive feedback on correlations that we need. So we can model this in a system of masses connected by springs, and the masses can be in two positions, up or down, and the springs push them apart. So connected masses, if one is up, the other one wants to be down. So if they're both up, the spring is in tension. And the springs which are in tension are going to weaken or deform because they're not perfect springs. If they were perfect springs, then the history of the state configuration wouldn't impact the future dynamics of the system. You know, that was yesterday and now it's today, we're back, the springs haven't changed. But if the springs are imperfect, they differentially weaken or deform under stress, then some of those connections give way a little bit, whereas other connections don't. Which ones change and which ones don't depends on the past configurations that the system has visited. They change in proportion to the stress that they're under. So Chris Buckley's modeled that in large systems of particles connected by springs, where the springs are only changing in a way that's the differential easing of frustrations between the particles. They're just imperfect springs. And that means that this model of feedback between relaxing the state variables to find a local optimum, using the local optimum as a pattern for the correlation learning, that correlation learning step can be replaced by just relax the springs. So we have the state dynamics, which are relaxing the states and finding the patterns, and relaxing the springs changes the dynamics of the system and we go around again. However, it's important that there's pulse, that the state variables are repeatedly randomized and relaxed, or that the system experiences episodic stress of some kind. If that doesn't happen, then the particles relax to a local optimum, and then the springs relax to accommodate that local optimum, and then that's it. That's the only place you can ever go. The first thing you ever do is the only thing you can ever do. But if the system is perturbed so that it visits a distribution of local optima, then the changes in the springs don't just model where they've been, but they generalize over that in a way which increases the basin attraction of the global optimum as well. That's what I mean by adaptation by natural induction. So here's some more things that would be nicer if they had cool graphics. So these are the energy minimization trajectories of a system of particles and springs. You start them at a random initial configuration and they relax down to a local minimum. We're interested in those red dots at the end that positions the quality of the local minima. Let's zoom in on those. Here's many more local minima. The total energy of the system at local attractors for 1,000 samples without learning. Now, when we allow the springs to differentially weaken, this is what happens, that we start off with the same distribution, but the system very quickly converges on, so eventually it only has one attractor, which is an attractor that's a good solution to the original constraints. It learns to find good solutions more reliably with experience. In some kinds of systems, it can find something that is better than anything that was found without learning, and as we increase the size of the system, we find that it converges on something which was way better than anything that was found without the learning. So that's only possible because the network is doing generalization. If you're familiar with, from the GA literature, such as the CMAES, it's doing the same sort of thing. It's learning correlations and using those learned correlations to explore the space differently so that it has different attractors. So that completes the connection from networks of viscoelastic connections to global adaptation ability. And that applies equally well to particles connected by springs or other kinds of networks where connections give way under stress. So there's no natural selection here. There's no differential reproduction of entities in a population, not the nodes, not the links, not the network as a whole. And it's possible because the change in the connections is directional. It changes in the direction that reduces the energy of the system, not increases the energy of the system. That's why you get positive feedback on correlations, not negative feedback on correlations. When you stretch a spring, when you hold a spring in tension, its natural length changes. Which way does it change? It changes in the way that makes it more comfortable with the way that you are forcing it, not less comfortable. And that directed change is what Dawkins didn't see. Right? He assumed that change could never be directed in a way that was meaningful by the environment, but this shows that it can. Okay, so that means that the universality assumption of Darwinism is incorrect. Natural selection is not the only process capable of producing adaptation spontaneously without being designed or selected for that purpose. It only requires connections that give way slightly under stress and pulse, that episodic experience or stress. Working with Tim Lewins to describe a paper on the incorrectness of universal Darwinism. Now, those conditions can be met in Hebbian learning in neural networks or mechanical viscoelasticity in springs, but also in self-interest acting on relationships in a society. If my friendship with you causes frustrations on my behavior, I become less friendly with you, so you influence me less, right? Or in interspecific interactions in an ecosystem, the connections between species in an ecosystem, and here, the thing that's changing the connections is natural selection, but what's going on at the system level is natural induction. Even when selection is involved, it's a different adaptive process because it applies in systems where selection doesn't. Selection applies at the individual level of individuals within each species, not at the system level because the system doesn't reproduce. So the interaction of natural selection and natural induction is complicated and interesting because biology is full of dynamical systems that are described by networks, and often the links can change over time, i.e. the interaction coefficients can change under natural selection. And if you let natural selection modify connections, it does so in a manner that eases frustrations and produces positive feedback on the patterns that are already there. So let's look at a model that does that. This is a model of changing interactions in an ecosystem, multiple species in an ecosystem. So the state variables are the species densities, and the interactions are the competition coefficients between species. And Dan says, well, we should be able to get this to solve problems like we did in the Hopfield model. And he says, we can set the initial competition coefficients to represent the constraints of a resource conflict problem. Which problem should we use? Well, we could have used a random pairwise constraint problem like we did for the neural networks, but Dan said that was boring. Let's do it with Sudoku. So the initial constraints between species means species number 5 in the first cell has strong competition coefficients with all the other numbers in the same cell, because you only want one of them to be high density at the same time. And it also has strong competition coefficients with other 5s in the same row or the same column or the same box. Can an ecosystem learn to solve Sudoku? So we set the initial species densities to something random, and there's lots of conflicts shown in red. We run the Locker-Volterra dynamics, and it finds a configuration where there's slightly less conflict, right? That's a locally optimal solution to the rules of Sudoku. The climax community of the ecosystem is a locally optimal solution to Sudoku. And if we were to leave it there, then and allow natural selection to modify the interaction coefficients between species, that's individual level natural selection, not group selection, then it would simply reinforce that climax community, and then in future the only place it would ever go would be to that particular solution. But if we apply regular shocks whilst the interactions evolve slowly, then when we come back later and have another look, we can start from the same initial random pattern where there's lots of conflict, but now the dynamics of the Locker-Volterra system take us to somewhere else. They take us to a configuration where many more of the conflicts between species have been solved. It has systemic intelligence in so much as it's not that the individual species have got smarter, but that the system as a whole knows where to find solutions in the system. It knows how to resolve those conflicting constraints and find more harmonious states, even for very hard, difficult Sudoku problems that humans basically can't do. So ecosystems are not supposed to be able to solve problems. There's no selection at the system level because there isn't a population of ecosystems. But it is a dynamical system described by a network of viscoelastic connections, and when subject to episodic stress or occasional shock, it adopts adaptive organization, not by natural selection, but by natural induction. So this suggests conditions exist where the biosphere could have adaptive organization, like the Gaia of Jim Lovelock, but much more than just homeostatic self-regulation. Right? Solving Sudoku problems is more intelligent than just keeping your temperature cool. Note that the shocks or perturbations are essential, and in different natural systems that might occur on different timescales, a sustained pressure will simply canalize the current solution and wipe out the history of the system. I think I probably should skip a little bit here to talk about how natural induction works over multiple levels. So we're familiar with the evolutionary transitions in individuality, such as from single cell to multi-celled organisms. And there's a way in which natural induction at one level of organization can then prime the working together that is necessary for the instantiation of natural selection at the next level of organization, which would then implement a network of entities that can participate in natural induction at the level above and so on. And this gives us a model of deep evolution where the transitions in individuality are no longer just fortuitous happenstance. They're not dumb luck, as they say, but they are increase in the systemic intelligence of communities which become individuals at the next level of organization. By the way, from an engineering point of view, if you're interested in solving optimization problems, you don't really need to use a population at all. You can do it as a learning algorithm, but you can do it through these multiple levels of organization, and it gives you an optimization algorithm that is superior to state-of-the-art model building optimization algorithms. So lastly, a quick chat about the implications. So in social systems, the same principles extend. Each individual is, through individual utility maximization, motivated to change relationships with others to maximize their individual utility. And if the system experiences shocks or episodic stress, then the organization of those connections will increase long-term collective welfare. The society can have adaptive organization without top-down governance, increasing the total utility of the system, much like the invisible hand of Adam Smith, but much more than simply finding the local Nash equilibrium, more like a theory to support Ellen Ostrom's social ecological systems, a framework of collective self-governance with multiple layers of nested enterprise. Now, the prime mover behind natural selection is differential survival and reproduction, separating those that win from those that lose, or those that grow the fastest from those that don't. But the value system that derives from that, if you believe that natural selection is the only possible way that something could get better by itself, then competition and self-interest are not just unavoidable facts of life, but they're actually necessary and desirable for improvement and progress. And that changes, that slides from a scientific observation of what is to a value system of what ought, that changes our choices and actions, that competition and self-interest is desirable. That leads to a Western worldview where survival of the fittest becomes a worldview which drives unlimited growth and excuses discompassion and exploitation of one another and natural resources, a drive which is behind all of our greatest global challenges. There's a different worldview, of course, more familiar in the Eastern wisdom traditions, that sees a larger tapestry of living things, a harmonious web of life, if you like. And in this view, there's no aim to win or outcompete others, only to find harmony with nature, to live with greater ease and balance, playing a relatively humble role, contextualized within a greater whole. That worldview is more consistent with the idea that cooperation and synergy and working together with respect for nature and one another is natural and wise. Everything is connected. Love is the way. Now, returning to that prime mover for natural selection, what's the prime mover for natural induction? Whereas for selection, it's about segregating or separating those that win from those that lose. In natural induction, it's the differential easing of relationships. It's a mechanism of transformational change, not variational change in Elliott-Sober's terminology. It has a flavor of connectedness. Adaptation by natural induction isn't driven by survival and reproduction of entities. It's driven by the differential easing of relationships between them. And the systemic intelligence of the system isn't held in the parts, but in the conditioned relationships between them. It's not about competition, survival, and selfishness. It's about relationships, connectedness, and organization. So, natural induction doesn't say that all life is lovely and harmonious. In fact, it enables us to transfer the rigorous principles of distributed learning theory to tell us what the conditions are that will enhance systemic intelligence and what the conditions are that would make it worse. But it is compatible with a worldview that sees our relationships with one another and with nature not just as resources to be exploited and opportunities to benefit ourselves, but as connections that hold collective knowledge accumulated by past experience. It's those relationships that make the whole smarter than the sum of the parts, and perhaps that perspective encourages a worldview where we want to treat our relationships with each other and nature with some suitable reverence. And if you want to know more about that way of thinking about things and how that fits together, I'm teaching a course through programs in Earth Literacies starting in May. Entitled What's Love Got to Do with It? From Survival of the Fittest to Compassionate Connection. And these